You think you know what big is. That's the first problem. You've been walking around your entire life with a sense of scale that the universe finds, frankly, insulting. You know what a mountain is. You've seen the ocean. You've maybe stood at the edge of the Grand Canyon and felt that particular vertigo that tells you your brain was not built for this, and you thought, well, that's the limit. That's where the human nervous system cashes in its chips and says, I was not designed for anything larger than this. And you went home. And you were wrong. You were wrong in a way so profound, so foundational, so completely embarrassing that by the time I'm done tonight, you will never look at the sky the same way again. And I mean that not as a promise of wonder, though it is that too. I mean it as a warning, because some things, once you've seen them clearly, cannot be unseen. Let me start with the Sunday. I want you to hold the sun in your mind for a moment, not as a metaphor, not as a symbol, but as a physical object. It is a sphere of hydrogen and helium plasma. It has a diameter of 1.4 million kilometers. If you wanted to drive around its equator at highway speed, let's say 100 kilometers per hour, like you're on a good German Autobahn, it would take you 16 years. 16 years of driving, no stops, not sleeping, just driving to circumnavigate the sun at the equator. That same sun is so massive that it contains 99.86% of all the mass in our entire solar system. Every planet, every moon, every asteroid, every comet, every fleck of dust between here and the Oort cloud and the sun outweighs all of that by a factor of more than 700. Our entire solar system is a rounding error on the sun's bathroom scale. I want you to feel that. I want that to land. Because the thing I'm about to tell you will only work if that foundation is solid. The sun is monstrous. The sun is incomprehensibly large by any standard that biology has prepared us for, and it is a dwarf. It is a small, unremarkable, middle-aged, yellow dwarf star, and compared to what exists in this galaxy, it is a grain of sand. Now here is where it gets strange. There is a constellation in our southern sky called Scutum the Shield. Not one of the glamorous constellations, not Orion with his belt and his mythology, not the Southern Cross, not the Scorpion. Scutum is small and obscure, and you would not notice it unless you were looking for it. And within that constellation, roughly 20,000 light years from where you're sitting right now, 20,000 light years, meaning light, which travels 300,000 kilometers every second, would take 20,000 years to make the trip. There is a star that has no earthly right to exist. Its name, for the purposes of astronomy, is Stephenson 2 to 18. It was named not for any grand discovery, but because it sits in a star cluster cataloged by a man named Charles Bruce Stephenson in the 1970s, a quiet, methodical astronomer who was doing patient survey work in Ohio and had no idea he was pointing his telescope at the largest object that any human being has ever identified. Stephenson 2 to 18 has a radius approximately 2,150 times the radius of our sun day. I want you to sit with that number. Not just hear it, sit with it. If you took Stephenson 2 to 18 and placed it at the center of our solar system, where the sun currently sits, its surface would extend past the orbit of Saturn. Not Mercury, not Venus, not Earth, not Mars, not Jupiter, Saturn. Saturn, which orbits the sun at a distance of 1.4 billion kilometers. The surface of this star would engulf everything between us and Saturn. Earth would be inside the star. Mars would be inside the star. The asteroid belt would be inside the star. Jupiter, the largest planet in our solar system. A world so massive that all the other planets combined could fit inside it with room to spare. Jupiter would be inside the star. The four great moons of Jupiter that Galileo discovered in 1610, and that permanently ended the idea that everything in the cosmos revolves around the Earth. All of them would be inside the star. You would have to travel another 300 million kilometers beyond Jupiter's orbit before you reach the surface. I'm going to give you a thought experiment now, because I find that the numbers alone don't do the job. Our brains did not evolve to process numbers like 2,150 solar radii. Evolution equipped us to track predators, estimate distances across a savanna, judge whether a fruit is ripe. It did not equip us to genuinely feel the scale of a hypergiant star, and any teacher who tells you they can make you feel it by just reciting numbers is lying. You need an analogy. You need something to grab. Imagine a standard basketball. That basketball represents our Sunday. Now, under this analogy, where is Earth? Earth orbits the Sun at a distance of about 109 solar diameters. So Earth is roughly a peppercorn sitting about 10 meters away from your basketball. And how big is Earth itself? On this scale, Earth is a speck about 2 millimeters across, barely visible, smaller than a grain of sand. Under this same scale, what is Stephenson 2 to 18? It is a sphere with a radius 2,150 times larger than our basketball Sunday. That's a sphere roughly 12 meters across, a sphere the size of a small house. And our solar system, our Earth, our moon, Mars, the asteroid belt, Jupiter, Saturn, all of that fits inside the first 12 meters of radius. So everything that any human spacecraft has ever visited, every place any human being has ever contemplated going, sits inside this star on our scale model. We would be inside it. All of human spaceflight would be inside it. All of our planetary ambitions would be inside it. That's not a metaphor. That's not poetry. That's the geometry. Now, I should tell you something. For most of my career, and I've been thinking about stars for more than 50 years, when people asked about the largest star, the answer was VY Canis Majoris. VY Canis Majoris sits in the constellation of the Greater Dog, about 3,900 light years away. It is a red hypergiant. For decades, estimates of its radius put it somewhere between 1,400 and 2,000 solar radii. And it was the reigning champion, the heavyweight title holder, the thing you put on the poster when you wanted to show an audience the scale of stellar physics. I used VY Canis Majoris in lectures. I described it with the same kind of numbers I just gave you. And it turns out this is what science does. This is the process. This is why I love it, and sometimes want to throw things. It turns out the measurements were uncertain. The radius of a star, 3,900 light years away, is not something you can simply read off an instrument. You infer it. You calculate it from brightness and temperature and distance, and every one of those quantities has an error bar. And error bars compound, and the truth is that the community had been systematically overestimating VY Canis Majoris. More recent measurements suggest its radius is closer to 1,400 solar radii, still extraordinary, still the largest thing most people can process, but no longer the record holder. And then there's UY Scuti, sitting in our same Scutum constellation, which was first cataloged in 1860 by the Bonn Observatory. During a sky survey, they listed it as a variable star, which it is, a pulsating star that changes in brightness over cycles, and they had no idea what they were looking at. A century and a half later, we measured it at roughly 1,700 solar radii, and for a few years it held the title. And now there is Stephenson 2 to 18 with its 2,150 solar radii, and I will tell you honestly, I am not certain it will hold the record forever. There are other candidates. There is WOHG 64 in the Large Magellanic Cloud, our companion galaxy, which may be comparable. There is the simple fact that we have not looked at everything, that our galaxy contains 400 billion stars, that our measurements at distances of 20,000 light years carry uncertainties that could humble anyone. But it is the best we have, and the best we have is staggering. Now here is where it gets strange again. I need you to understand something about how we measure the size of a star, because this is not a trivial thing. You cannot point a ruler at Stephenson 2 to 18. You cannot send a probe out there. What you can do, what astronomers do, is measure the star's luminosity, which is its total power output, and measure its surface temperature, and then use a law of physics called the Stefan-Boltzmann relation, which tells you that the power radiated by any hot object depends on its surface area and its temperature. If you know how bright something is and how hot it is, you can calculate how big it is. This is elegant. This is physics working exactly as it should, but it requires that you know the distance to the star, because brightness, as we observe it, falls off with the square of distance. And if your distance is wrong, your luminosity is wrong, And if your luminosity is wrong, your radius is wrong. And measuring distances to stars 20,000 light years away is genuinely hard. We use parallax for nearby stars, the same principle you use when you hold up a finger and alternately close each eye, watching the finger jump against the background. For stars close enough, as Earth orbits the Sun, we can measure that angular shift and calculate the distance exactly. But at 20,000 light years, the parallax angle is so tiny as to be almost unmeasurable. And we use other methods, the properties of the star cluster it belongs to, the dust and extinction between us, and it, spectroscopic parallax. These methods are good. They are not perfect. And so when I tell you Stephenson 2 to 18 is 2,150 solar radii, understand that this number carries an uncertainty. It might be 1,900. It might be 2,300. The error bars don't change the conclusion. This is the largest known star, but they are real. And anyone who gives you a number without an error bar is not doing science. They are doing decoration. Now I want to talk about why these stars exist, because that's where the physics gets beautiful and almost unbearably strange. A star is, at its most fundamental level, a negotiation between gravity and pressure. Gravity wants to pull everything inward. It always wants to pull everything inward. Gravity never takes a day off. And what prevents a star from collapsing under its own gravity is the pressure generated by nuclear fusion in its core. The energy released when hydrogen nuclei smash together hard enough and hot enough to overcome their electromagnetic repulsion and fuse into helium. This energy pushes outward, gravity pulls inward. When the two balance, you have a stable star, and our sun has been in this state for about 5 billion years and will remain in it for another 5 billion years. This is called hydrostatic equilibrium, and it is one of the most elegant balancing acts in nature. But the story doesn't end there. Now think about what happens when a star is much more massive. And by much more massive, I mean not just double the mass of our Sunday, or 10 times, but perhaps 50, 60, 100, even 200 times the mass of our Sunday. These objects exist. The most massive star we've measured, a blue star called R13601, sitting in a vast star-forming region in the large Magellanic Cloud called the Tarantula Nebula, about 160,000 light years away, has a mass somewhere between 170 and 300 times the mass of our Sunday. The uncertainty is large because it's very hard to weigh a star, but this thing exists, and it is crushing itself under its own gravity with such ferocity that the fusion reactions in its core are going at a rate that produces more light, more energy, more radiation than 250,000 suns combined. The luminosity of a very massive star is not just proportional to its mass. It scales roughly as the cube or fourth power of mass, depending on the regime. In plain terms, a star twice as massive as another doesn't shine twice as bright. It might shine 8 times as bright. This relationship has a consequence. There is a limit worked out by Arthur Stanley Eddington in the early 20th century, and one of the great theoretical achievements of astrophysics called the Eddington luminosity. It is the maximum luminosity that a star can have while still holding itself together. The physics is simple and brutal. Radiation carries momentum. When light pushes outward through a star, it exerts pressure on the surrounding gas. If the star is luminous enough, the radiation pressure on the outer layers exceeds the gravitational force pulling those layers in, and the outer layers are expelled. The star tears itself apart with its own light. Eddington showed mathematically where this limit lies, and it depends on the star's mass and on the opacity of the stellar material, how efficiently the gas absorbs radiation. For stars approaching the Eddington limit, the outer layers are so precarious that the slightest perturbation can launch them into space, and this is exactly what we observe. The most luminous stars are also the most unstable, the most variable, the most prone to episodic mass ejection on scales that beggar imagination. Eta Carinae is the example I keep coming back to, not because it's the largest star, it isn't, but because it showed us what stellar physics looks like at the extreme. Eta Carinae sits about 7,500 light years away. In 1837, it began to brighten, and it brightened and it brightened until in 1843, it briefly became the second brightest star in the entire sky, the second brightest point of light visible to the naked eye, outshone only by Sirius, the most prominent star in the night sky. And then it faded. The event is called the Great Eruption, and in the course of that eruption, Eta Carinae expelled somewhere between 10 and 40 solar masses of gas in a period of about 2 decades. Not years, decades. Not a single explosive event, but a sustained, violent, almost unimaginable exhalation of stellar material. The ejected material is still expanding today. We can see it. It forms two enormous lobes of gas and dust surrounding the star, called the Homunculus Nebula, the Little Man Nebula, for its vaguely bipolar shape, and those lobes are now about 1.5 light years across. And Eta Carinae didn't die. It's still there, still luminous, still unstable, still sitting there in the galaxy being a problem. I've been thinking about Eta Carinae for 30 years, and it still makes me uneasy in a way I find productive. It tells you that a star near the Eddington limit is not a stable object in any sense that word means. It is a barely constrained explosion, held together by gravity, continually testing the boundary between star and supernova. Now, here is the thing I need you to understand, and this is the part that most people get wrong. The biggest stars are not the most massive stars. Mass and size are not the same thing, and in stellar physics, they can be almost entirely decoupled. R13601, with its 170 to 300 solar masses, has a radius of perhaps 30 to 40 solar radii. It is large. It is not Stephenson 2 to 18 large. It is not even close. Stephenson 2 to 18 is far less massive, probably somewhere between 10 and 30 solar masses, though I want to be honest that this estimate is uncertain, and yet it is 50 times larger in radius than R13601. Why? Because Stephenson 2 to 18 is a red supergiant. And the secret to understanding red supergiants is understanding what stars do when they get old. When a star has burned through most of the hydrogen in its core, the core begins to contract. There's less fuel, less fusion, less pressure pushing outward, and gravity begins to win the negotiation. The core heats up as it contracts. But here is the paradoxical thing. As the core contracts and heats up, the outer layers of the star expand dramatically. The star becomes simultaneously denser in its core and vastly more extended in its outer envelope. The surface moves outward, cooling as it goes, until the star has a surface temperature of perhaps 3,000 to 4,000 Kelvin, cool enough that it glows red rather than white or yellow, and the radius has expanded enormously. The star has become a red giant, or in the most extreme cases, a red supergiant, or even a red hypergiant. This is what Stephenson 2 to 18 is. It is a massive star in a late stage of its evolution, a star whose core has contracted while its outer atmosphere has puffed out to dimensions that make any earlier conception of large seem quaint. The outer layers of Stephenson 2 to 18 are so loosely bound that the surface gravity is extraordinarily weak, perhaps a few millionths of Earth's surface gravity. If you stood on the surface of this star, which, to be clear, you cannot, because there is no solid surface, because it is a diffuse gas at temperatures of about 3,200 Kelvin, and because the radiation would destroy any structure made of matter that we know how to build. But if you could somehow exist there, you would need essentially no effort to escape. The escape velocity from its surface is hundreds of times lower than the escape velocity from Earth. This star is, in a physical sense, barely holding its outer layers at all. Now, here's where it gets strange one more time, and I mean it this time more than the others. Think about what it means for a star's outer atmosphere to be so tenuously held. It means the star is losing mass. All stars lose mass. Our own sun ejects about 1 million tons of material per second in the solar wind, but the rate at which a red hypergiant like VY, Canis Majoris, or Stephenson 2 to 18 sheds its outer layers dwarfs anything our sun does by factors of millions. VY Canis Majoris has been measured losing mass at a rate of roughly 3x 10 to the power of -4 solar masses per year. That is, every year it ejects into space a mass of material comparable to 1/3 of a thousandth of the sun's total mass. That sounds small until you realize the sun's mass is 2 times 10 to the 30th kilograms, 2,000 billion kilograms, and you're ejecting 1/3 of a thousandth of that every year. VY Canis Majoris is dissolving, not quickly by human standards. It has been doing this for hundreds of thousands of years and will continue for some time, but it is actively shedding itself into the surrounding space, creating an enormous nebula of expelled material that can be detected in radio and infrared observations. We can see the shroud it is weaving around itself. We can watch a star building its own cocoon. And what happens when the core, having burned through hydrogen and then helium and then carbon and neon and oxygen and silicon in the onion shell structure of a dying massive star, finally runs out of fuel? It cannot sustain the pressure. Gravity wins. In a fraction of a second less time than it takes you to blink, far less time, perhaps 1/10 of a second, the core collapses. A core that was once the size of Earth compresses to a sphere perhaps 20 kilometers across. 20 kilometers. Smaller than the distance between here and the edge of this city. The density it reaches is so extreme that atomic nuclei are crushed together, electrons are forced into protons, and the entire object becomes a neutron star, a ball of neutrons more massive than the sun, packed into a volume smaller than a city, rotating perhaps hundreds of times a second. The infalling outer layers of the star hit this newly formed neutron star, bounce, and are hurled outward at a significant fraction of the speed of light. The star explodes in a core collapse supernova. For a massive enough star, and there is still genuine scientific debate about exactly where the threshold lies, the core doesn't stop at a neutron star. It keeps collapsing past the neutron star density and forms a black hole, a region of space-time so curved that not even light can escape. And the explosion may be not just a supernova, but a hypernova, a blast of energy 10 or 100 times more powerful than a conventional supernova, sometimes accompanied by a gamma-ray burst, a beam of high-energy radiation so powerful that if it were directed at Earth from a few thousand light years away, it could strip away the ozone layer and sterilize the surface of our planet. Gamma-ray bursts are the most energetic events in the known universe. They are the death screams of the most massive stars. I want to be clear about something here. We do not know with certainty what Stephenson 2 to 18 will do when it dies. Stars in this mass range, the red supergiants, the hypergiants, are not well understood at the level of detail we would like. The stellar evolution models are good, but the models struggle at the extremes. We do not know exactly how much mass Stephenson 2 to 18 has shed because we cannot observe it with sufficient resolution and sensitivity. We do not know precisely what nuclear burning phase it is currently in. We have a broad outline. It will eventually exhaust its fuel, its core will collapse, and there will be a cataclysm. Whether that cataclysm produces a visible supernova, or whether the star simply implodes, and we have actually observed candidate events where a massive star apparently just vanishes, we do not know. That uncertainty is not a failure of science. It is the frontier. It is the place where the questions are still alive. I want to tell you about a morning in the late 1970s when I sat with a colleague and we went through what were then the best stellar evolution models, trying to understand why the distribution of massive stars on the Hertzsprung-Russell diagram, the plot of stellar luminosity versus surface temperature, that is one of the fundamental tools of astrophysics, showed a striking absence in the upper right corner. The upper right corner represents stars that are both extremely luminous and extremely cool. which is to say extremely large. There were essentially no stars there. This is called the Humphreys-Davidson limit, after Roberta Humphreys and Chris Davidson, who published a landmark paper in 1979 establishing this observational boundary. What it means is that there is an effective upper limit to how large and luminous a star can actually be while remaining stable. Stars that try to occupy that region of the diagram are unstable. They shed mass violently, they pulsate, they have eruptions. They cannot maintain that configuration. The physics conspires to prevent it. And yet, within that constraint, within that complex interplay of radiation pressure and gravity and mass loss and opacity and convection, nature has managed to produce Stephenson 2 to 18. Nature has, within the rules it imposes, found a way to build something of incomprehensible scale. The star is near the edge of what is physically permissible. It is almost certainly going to shed significant mass before it dies. It may already be doing so, but it exists right now, tonight, 20,000 light years away, with a volume roughly 10 billion times the volume of our sun, radiating energy at a rate perhaps 100,000 times the solar luminosity, sitting in its cluster like an engine that has been running at full throttle for millions of years and is starting to overheat. I want to make a connection now that I think is usually left out of these conversations, because people treat stellar astrophysics as if it were a category separate from everything else in physics, and that is a mistake. Every atom in your body, heavier than hydrogen, was made in a star. Every atom heavier than iron in your blood contains iron, your bones contain calcium. Every cell in your brain runs on sodium and potassium and phosphorus. Every atom heavier than iron was made in the explosion of a massive star. Iron and everything lighter than it can be synthesized in the core of a sufficiently massive star through the successive burning stages I described earlier. Hydrogen, helium, carbon, neon, oxygen, silicon, and finally iron. Iron is where the party ends, because fusing iron costs energy rather than releasing it. And once the core is iron, the fusion engine stops. But the heavier elements, the gold in your jewelry, the uranium that powers nuclear reactors, the iodine your thyroid gland requires to function, the strontium and barium in your bones. These elements are built through rapid neutron capture, the R process, which happens in the extreme conditions of a core collapse supernova, or in the merger of two neutron stars. They are scattered into the interstellar medium by the explosion. They get incorporated into molecular clouds. The molecular clouds collapse under gravity to form new stars. The new stars have planetary systems. The planets condense from material that includes these heavy elements. Life develops on a planet like Earth. And 4 billion years later, a primate is sitting in an auditorium made of atoms that were forged in the deaths of stars. The largest stars are the most productive element factories in the galaxy. A star like Stephenson 2 to 18, when it finally dies, will release into the surrounding space a quantity of heavy elements that will enrich its region of the galaxy for billions of years. Generations of future stars will form from material enriched by its death. Those stars will have planetary systems. And the atoms from Stephenson 2 to 18 will eventually, after timescales that make all of human history look like a rounding error, find their way into chemistry, into biology, into whatever forms of complexity the universe has in mind for a region of space that currently contains only darkness and dust and a dying hypergiant. You are, in the most literal physical sense, made of stardust. This is not a metaphor. This is nuclear physics and stellar evolution and chemistry and biology, all in a chain, unbroken, from the first moments of the universe to right now, to this room, to you. And the largest stars, the ones that burn hot and fast and die young in cosmic terms, are disproportionately responsible for this enrichment. The sun, bless it, will not produce heavy elements in any significant quantity. It is too small. It will become a white dwarf and fade gently. The massive stars are the ones that do the real chemical work. The massive stars are the ones that die violently enough to scatter their contents across the galaxy. And the largest stars, the red supergiants and hypergiants, are the stars whose outer layers are so diffuse and so weakly bound that they enrich the interstellar medium even before they die, shedding their outer shells over hundreds of thousands of years. I have one more thing to tell you before I'm done, and I want you to pay close attention because this one keeps me up at night. We do not understand, at the level of detail that would satisfy me, how red supergiants get as big as they do. The broad strokes of the story I've told you, core contracts, outer layers expand, star becomes a red supergiant, are well established. But the physics of the outer envelope of a red supergiant, the convective processes that transport energy outward through these bloated outer layers, the pulsations that cause the star's size and luminosity to vary, the mechanism by which mass is driven off the surface at the rates we observe. These are areas of active, unresolved research. The models we have are genuinely good. They are not good enough. When we try to simulate the outer layers of a star like VY, Canis Majoris, or Stephenson 2 to 18, we run into what is diplomatically called challenges, which is the scientific community's way of saying our models break down and we're not sure why. Part of the problem is convection. In the outer layers of a red supergiant, convection, the process by which hot gas rises and cool gas sinks, carrying energy outward, the same way boiling water carries heat, operates on scales that are simply enormous. The convective cells in our sun are on the order of thousands of kilometers across. The convective cells in a red supergiant may be comparable to the entire radius of our solar system. These are not small corrections to the model. These are the dominant physical process, and we do not have a fully satisfying theory for how to model them. We use approximations. The approximations are imperfect. The stellar structure models are therefore imperfect. And when I say imperfect, I don't mean wrong. I mean that there are quantitative uncertainties that are large enough to matter, and we know they are there, and we have not yet resolved them. This is not embarrassing. Or rather, it's the right kind of embarrassing, the kind that means you're working on something real and difficult, not the kind that means you've made a mistake. The fact that we can measure the size of a star 20,000 light years away to within a factor of 20 or 30% is, when you think about it, a stunning achievement of human ingenuity. 100 years ago, we didn't know other galaxies existed. 50 years ago, we were still arguing about the distance to the Magellanic Clouds. Now we are measuring the radii of individual stars in the inner disk of the Milky Way and finding that one of them is larger than the orbit of Saturn, and arguing about whether it's 1,900 solar radii or 2,300 solar radii. The argument itself is a form of progress. But I want you to leave here tonight with the appropriate combination of wonder and humility. Wonder, because there is a star 20,000 light years away that would engulf this entire solar system, that radiates as much energy in 1 second as our sun radiates in 10 years, that is in the process of dissolving itself into the interstellar medium and will eventually die in an explosion so powerful it could be visible in daylight from a neighboring galaxy. That is real. That is happening right now. The light from Stephenson 2 to 18 that we observed and measured left that star 20,000 years ago, when humans were painting animals on the walls of caves in southern France. And the star itself, what it is doing at this precise moment in time, we have absolutely no way of knowing. It may still be there, burning and pulsating and shedding mass into the surrounding space, or it may have already died. The supernova may already have happened, and the light from that explosion is somewhere out in the dark between there and here, traveling toward us at the speed of light, still 10,000 or 15,000 years away. And in 10 or 15,000 years, some successor species to this one or this species, if we are very lucky and very wise, will look up and see a new light in the constellation of Scutum and say, something just died, and measure its spectrum and confirm what I've been telling you tonight, that a star so large it would swallow our world without noticing has finally stopped holding itself together in humility, because we do not have the theory fully in hand. We do not know exactly why these stars get as large as they do and no larger. We do not know with certainty what any specific hypergiant will do when it finally exhausts its fuel. We do not know what fraction of them form black holes rather than neutron stars, and whether the ones that form black holes do so quietly or catastrophically. We are standing at the edge of what physics currently understands, and what lies beyond that edge is not nothing. It is more questions, deeper questions, questions that will occupy the best minds in astrophysics for the next century. And here's the thought I want to leave you with. The Milky Way contains something like 400 billion stars. Of those 400 billion stars, perhaps a few hundred, maybe a few thousand, we're not sure are red supergiants or hypergiants comparable to Stephenson 2 to 18. They are rare. They are brief, these objects. On astronomical timescales, live for only a few million years. A fleeting moment compared to the 10 billion year lifetime of a star like our Sunday. They are violent and unstable and in the process of destroying themselves. And they are necessary. The universe does not produce complexity, does not produce chemistry, does not produce biology, does not produce any of the beautiful and intricate structures we see in the cosmos and in ourselves without these violent, short-lived, enormous engines doing their work. The largest stars are the universe's most extravagant method of making something. They burn prodigiously, they die catastrophically, and they leave behind the material from which everything interesting is eventually constructed, including you. You are sitting in this auditorium because billions of years ago, a star far larger than our sun ran out of fuel and exploded and scattered its contents across the galaxy. Some of those contents became part of the molecular cloud that collapsed to form our sun and its planets. Some of those atoms became the surface of the earth and the oceans, and eventually the chemistry that gave rise to life. And here you are, a temporary arrangement of those atoms, sitting in a room of light trying to understand where you came from. The largest star ever discovered is a question mark, 20,000 light years away, asking you whether you're paying attention. I hope you are, because the universe does not explain itself twice.